Okay, I realized I used a title. In my title, I said chip away, and I don't think most people in Germany use that term. And basically, if you think about starting with a piece of stone, it's a kind of artistic metaphor where you chip away at the stone and you end up with the perfect statue. And the very famous myth of Pygmalion, where the statue is brought to life. And what I'm very interested in is ideas about biomimetics. Does everybody know biomimetics in here? Is there anyone? Biomimetics is really looking at the body carefully and applying knowledge from the body in the creation of new technologies. And bioabstraction is also looking closely at biological processes and so on, and abstracting those. So, for example, somebody like Leonardo was looking at bird flight. Well, bioabstraction gives us the airplane, so it's not exactly the initial shape. Okay, and so, now if I'm... All right, so about 12 years ago, I was in a situation in Switzerland. They were starting something called Artists in the Labs, where artists would work with scientists together and tackle research. In my own background, I studied at MIT. I studied at the Center for Advanced Visual Studies. Very early on, started working with interactive systems. So I was always interested in generative systems, how computers could work with this notion of generativity, emergent systems, so that as you used it, certain kinds of outcome would arise in their use. And I got more and more interested in how that could be applied to mind, brain, and study. I met Otto Rosler, who's probably best known for the Rosler attractor in chaos theory. He studied with Konrad Lorenz, so he studied ethology. He writes about endophysics, which is a physics from within, so it's kind of thinking about the biophysics of thought. And he's one of these rare people that moves all over the place. So when I met him, I said, Otto, what do you think about the idea of making an electrochemical computer? And he said, well, I started writing about that in 1970. So it was one of these things where we immediately had a discussion. And for almost 12 years, we would spend 1 hour per week talking. And this has culminated in a book called Neosentience, the Benevolence Engine. And neosentience is basically thinking about our human sentience. Our human sentience isn't usually talked about in terms of artificial intelligence and so on. And what we did was we began to build up a kind of theory. The book itself is a nonlinear book. It has about 300 chapters that move in many, many different directions. And instead of the Turing test, some of you might know this test for intelligence that Alan Turing made. We decided to make a kind of pragmatic situation so that we would say that if there was an autonomous robotic system, a learning system, this comes out of artificial intelligence, if it could satisfy a series of these criteria, we would say, for all practical purposes, it's a neosentient system. So one, it can learn, it can intelligently navigate, it can interact via natural language, which means in the way we're doing right now. It can generate simulations of behavior. It can think about potential behaviors before acting in physical space. So this comes from Konrad Lorenz. He talks about thinking is acting in, I'm not going to quote it right, sorry. It can function in a creative manner. It has a sense of play. It can come to have a deep situated knowledge of context through multimodal sensing. Its actions are informed by programmed drives and synthetic emotions, and it can display mirror competence. So obviously this is a very, very high bar to set, but interestingly enough, a lot of these things are sort of individually happening already in computer science. They're just not enfolded and brought together. And so I'm the person who does all the reading across fields, and I'm the person who learns enough in interdisciplinarity to be able to talk to somebody from their field. So I'm very honored to be here talking with you today about this. And so the definition of a computer, before 1935, a computer was a person. So if we immediately take that idea, instead of making a computer based on zeros and ones, then we think about how can I make a computer based on a person? Now, what's very interesting, like Arvid, I like to go back and point at kind of the first moments of things. Already in 1842, the first computer programmer, that was a woman, Ada Lovelace, who was the illegitimate daughter of Byron, which is very interesting. So there's a kind of funny, if you displace poetics and you mix it with mathematics, what do you get? Computer language. So Lovelace talked about machinic creativity through operational potentials. She says, the engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. It may be desirable to explain that by the word operation, we mean any process which alters the relation of two or more things, be this relation of what kind it may. This is the most general definition and would include all subjects in the universe. So this is a very, considering this is 1842 and thinking about computers, it's a very interesting idea. Now, of course, all of you know Kojal, who's kind of the father of neuroscience. But out of Kojal, Nicholas Reshevsky was very interested in mathematical biophysics and was very early on developing models of idealized biological processes. He happened to be the teacher of Pitts, of McCulloch and Pitts, and McCulloch and Pitts developed their first concept of the neural net. So it's basically, in terms of biomimetics, it's saying, let's look at what's at operation in the brain and how mind is arising, and let's theorize this, let's abstract this into a computational system. Now, Turing wrote about the automatic computing engine. So he talked about operative input and output organs. So again, here's this biological metaphor about intelligence, and he talks about a finite set of states of mind with the possibility of exploring groups. Heinz von Forster talks about cognition as being computations of computations. Now, this is very close to Arvid. William Clancy in the 1997, in his text on human knowledge and computer representations, he was kind of a proponent of this embodied embedded school. So in contrast to the symbolic approach, which I hereafter call the descriptive approach, the theory of situated cognition claims that when modelers equate human knowledge with a set of descriptions, such as a collection of facts and rules in an expert system, they're describing abstractly how the program should behave in particular situations. But they're not capturing the full flexibility of how perception, action, and memory are related in the brain. So I'm very interested in how the human being can very quickly shift contexts. We have very specialized computers that are very fast, but so far we've never had anything like the human being for the ability to bring disparate pieces of knowledge together and have an emergent sense that comes out of it. So this embodied embedded school, there's situated cognition, there's dynamic systems theory groups, second order cybernetics. I don't know if many of you are aware of the Macy conventions, where people from all different disciplines came together to talk about the beginning of cybernetics, the beginning of control and communication in the man and machine. So, but here the key idea is intelligent behavior arises out of an interplay between brain, mind, body, and world. And so again, it's very close to Arvid's sense. So the end-sentient paradigm, neo-sentient, the goal of the system exhibits a sentience of a new variety. It's self-organizing, environmentally embedded, nascent. The system is brought to life, and this is kind of a joke, not joke, but a kind of pun on being brought to life. Temporal, intraactive, and instead of interactive, intraactive is kind of being inside the other. So when we think about Piaget, when we think about language acquisition, which is a sub-branch of neuroscience, we are working together in a group of people that together inform each other. So linguistic practice is within a group as opposed to singular. So the idea is that this entity would be brought up, that it would learn this natural language. And we think in the same way we might bring up a child. Emergent, their actions arise in context and are not known in advance. navigational, that it can move about, and transdisciplinary in that the research is informed by many different domains. So this is what's kind of nice about the Neosentient project. It is looking very deeply at a human biofunctionality. So it's chipping away at, it's trying to always learn that next level of knowledge about what it is that enables us to operate for sentience to arise. How do low-level biological processes function in an emergent behavior, contributing to sentience production? What computational operations at all scale in the body contribute to sentience arising? How might these processes be abstracted? So when this idea of an analog, this idea of an analogy in the title of my paper, when you take a biological functionality and then you make an analogous functionality in the machine. What role does embodiment and memory play in this, and how can this best be articulated? How's my time going? 10 minutes? I have 5 left? Okay. So, given the vast complexity of brain-body environment set of relations, how can we best design new computational systems to support and or embody our research into human biofunctionality? One area that I'm very interested in is the creation of an electrochemical computer. The second side is the emulation of this in silicon. And this is, in the Neosentience book, is this model that Otto Rossler and I worked on for quite a long time. I don't know, in 5 minutes, I don't know if I can cover it, but basically it's a polysensing system, multimodal sensing. It's a real-time creation of VR. It's at the very top, synthetic emotions of attraction and repulsion. On the right-hand side is the ability to navigate and to either think about something or act in space. But as you can see, there are a series of loops, and they actually tie very clearly to the talk that we heard on Thursday night. These kind of loops of, like for example, in vision it builds up, but then it projects back, so you get this bi-directional stream of meaning production. So this system has a long-term memory, LTM there, short-term memory, pattern matching. It's a learning system, so it builds up knowledge about environment through multimodal patterning. Now, of course, this is a very rough system, so that's why it's interesting to be in conversation with neuroanatomists, people that understand neurophysiognomy at the deepest level. And so it's very exciting to say, okay, well, you got that loop wrong, or you got that loop right. You know, you can go through and really articulate things. So if we think about the body as an electrochemical computer, we might say there's languages of the brain. And so it's a mixed digital analog system. And when von Neumann was first working on computers in 45, around there, they decided, oh, well, we'll just go digital because all this analog stuff is too noisy. We can't control it. But what my contention is that there's something very special about the mixed variety of analog and digital signals in the body that enable us to have the kind of thought processes that we have. So an electrical language, language of synapses, spike trains, language of frequencies, brain waves, language of neurotransmitters, the lock key notion of shifting the efficacy of different neural processes. And then this debate about quantum level processes, which was my question the other night. Now, it's very interesting to note that Gordon Pask, already in 1961, a person who was both an artist and a scientist, began to work on chemical computers. And there was a whole biological computer laboratory that was set up in Illinois that had very interesting people there. There's some very good books about it. This was an initial drawing that Tim Sr. and Tim actually made the drawing, but this was an initial planning of an electrochemical computer. And there's a paper on my website, so I won't go into this now, there's not that much time. The idea of polysensing, that you might make a chip with multiple different sensors, the idea of grammars of attention, so that you might focus the attention in different ways of the entity. Integral, I've written a paper recently called The Engine of Engines Toward a Computational Ecology, thinking about how can we couple together many different kinds of computers that are each unique, like a DNA computer might talk to a quantum computer, might talk to a more standard computer. Could that maybe give us clues about how the body works? Then the whole notion of neuromorphic chips, the idea of all of the study of what you're doing, neuroscience being applied to the design of new chips. And there's a great deal of literature about that. And because there are so many problems, because there's so many questions, I've decided to work on a piece which is both an artwork and a scientific tool called the Insight Engine. And the Insight Engine is basically, it seeks to work toward the digital authorship of a tool to empower insight production, distributed interdisciplinary team-based research, and to potentially enable biassociational processes as discussed by Arthur Kessler. And I'm just going to very briefly show an initial drawing. Hello, go away, please. So when Rossler and I wrote the book, we made a compendium of ologies, or what were the major areas. And the idea was of this system is that you could choose one, choose another, and imagine now that this is tied to a whole database that relates to each of those, that you use computational linguistics and make comparisons. So the idea is to make a kind of biassociation engine. And I think that's where I'll end my talk. Is that about time? Thank you.